Welcome to this lecture on dosage calculations for medical assistants. Medication math can feel intimidating at first, but the good news is that most of what you need rests on a few clear steps and one simple formula. The goal today is to make you confident and, above all else, safe. We're going to focus on the calculations that matter most in the medical assisting role, and we are keeping this practical. Note that we are not covering intravenous medications or drip rates in this lecture. Those are outside our scope of practice here. Instead, we concentrate on the everyday calculations you are far more likely to meet, such as how many tablets to give, how many milliliters of an oral liquid to measure, and how to work with those doses that are based on a patient's weight. Here's the plan. First, we will talk about why this skill matters and where it fits in your role. Then we will review the units of measurement you will use and how to convert within the metric system, which is the foundation of almost every calculation. We will cover the common equivalents you should know by heart. Then we get to the heart of this lecture, the basic dosage formula, desired over half times quantity, and we will work through clear examples for tablets and for oral liquids. We will look at a second method, ratio and proportion, so you have a way to check your work. We will cover weight-based dosing, and we will finish with the safety habits that catch errors before they reach a patient. Keep a paper and pencil handy because the best way to learn this is to work along with me. Here are the 5 things you should be able to do by the end of this lecture. First, identify the units of measurement used in medication dosing because you cannot calculate a dose correctly if you don't understand its units. Second, convert within the metric system and between common equivalents, since a great many errors happen at the conversion step, and getting this right prevents most of them. Third, apply the basic dosage formula, desired over half times quantity, which is the single most useful tool in medication math and will handle the majority of the calculations you meet. Fourth, calculate oral and weight-based doses accurately, meaning you can figure out how many tablets or how many milliliters to give, and you can handle doses that depend on a patient's weight. Fifth, use safety checks to catch and prevent calculation errors because in medication math, the final step is always to ask whether your answer is reasonable and to verify before anything reaches a patient. Notice the progression. We move from understanding units to converting them to the formula to applying it and finally to checking your work. Don't worry if math has felt hard for you in the past. We'll go step by step, and by the end, you will have a dependable process you can trust. That process, more than speed, is what keeps patients safe. Let's begin with why this skill is worth learning well. In medication math, accuracy is not just about getting a good grade. Accuracy is safety. A calculation error can go 2 ways, and both are dangerous. If you give too little medicine, the patient may not get the benefit they need. If you give too much, the medication may cause harm, and with some drugs, the margin between a helpful dose and a harmful one is very small. Careful, methodical math is one of the most direct ways you protect patients. Notice the note on the left about children. Pediatric patients are especially vulnerable to dosing errors, in large part because their doses are frequently based on body weight and therefore require an extra calculation, which is an extra chance for a mistake. That's exactly why we will practice weight-based dosing later. Now look at where you, the medical assistant, fit in on the right. You prepare and measure ordered doses accurately, whether that is counting tablets or drawing up an oral liquid. You convert units when needed so that the provider's order and the medication label speak the same language. You develop the judgment to recognize when an answer simply does not look reasonable, such as a result that would mean giving a whole bottle at once. And crucially, you verify with the provider or the pharmacist whenever something is unclear or seems off rather than guessing. None of this asks you to prescribe or to decide the dose. It asks you to carry out the order precisely and to be an alert final check. That is the mindset to carry through the rest of this lecture. Before any calculation, you need to be comfortable with the units of measurement because a dose is meaningless without them. The great majority of medication math uses the metric system, so we'll put our focus there. Take a look at the table. The first row is the weight of the drug itself, meaning how much active medication is present. The metric units are the gram, the milligram, and the microgram, abbreviated lowercase g, lowercase mg, and lowercase mcg. You will see milligrams most often, as in 500 milligram tablet. The second row is the volume of a liquid, meaning how much fluid you are measuring. The metric units are the liter and the milliliter, abbreviated capital L and lowercase ml, and milliliters are what you will use constantly for oral liquids, such as 5 mLs of a syrup. The third row is the household system, which patients use at home, including teaspoons, tablespoons, and ounces. You need to know these because a patient may think in teaspoons while the medication is measured in milliliters, and part of your job is translating safely between them. Read the tip at the bottom because it captures a key relationship. A microgram is smaller than a milligram, and a milligram is smaller than a gram. The order from smallest to largest is micro, then milli, and then the base unit, either gram or liter. Fixing that order in your mind now will make the conversions on the next slide far easier because converting is simply moving between these units in a predictable way. Take a moment to get these units solid because everything that follows builds on them. This is the core skill that everything else depends on, so let's slow down and make it solid. Converting within the metric system sounds technical, but it follows one friendly pattern. Look at the steps on the left. 1 gram equals 1,000 milligrams. 1 milligram equals 1,000 micrograms. And 1 liter equals 1,000 milliliters. Notice that each step between neighboring units is a factor of 1,000. That single fact powers every metric conversion you will do. Now, how do you actually convert? Look at the two rules on the right. When you convert to a smaller unit, you multiply, and the number gets larger. For example, 2 grams becomes 2,000 milligrams because milligrams are smaller, so it takes more of them. When you convert to a larger unit, you divide, and the numbers get smaller. For example, 500 milligrams becomes 0.5 grams because grams are larger, so it takes fewer of them. A simple way to remember the direction is that smaller unit means a bigger number and a larger unit means a smaller number. Because each step is 1,000, converting is really just moving the decimal point 3 places, and thinking of it that way can make it quick. Finally, read the dark reminder box because it prevents a classic error. Always keep a leading zero, so you write 0.5, not just 0.5, and never use a trailing zero, so you write 5, not 5.0. Those decimal habits, which come straight from medication safety guidance, keep a dose from being misread by a factor of 10. Practice a few conversions until this feels automatic because the formula work ahead goes smoothly only when your units already match. These equivalents are worth committing to memory because they come up constantly and a good clinician recalls them instantly. Look at the table. 1 teaspoon equals 5 milliliters. 1 tablespoon equals 15 milliliters, which is also the same as 3 teaspoons. 1 ounce equals 30 milliliters. And very importantly, for weight-based dosing, 1 kilogram equals 2.2 pounds. Let's think about why these matter using the note at the bottom. Patients live in the household world. They think in teaspoons and tablespoons. But medications, especially liquids, are dosed and labeled in milliliters. If a parent hears take 1 teaspoon and reaches for a random kitchen spoon, they can easily give the wrong amount because kitchen spoons vary widely in size. This is a genuine and common source of pediatric medication errors. So part of your role is translation and education. You translate the order into the correct number of milliliters, and you teach the patient or parent to measure with a proper oral syringe or a marked dosing cup rather than their silverware. That one piece of teaching prevents real harm. The kilogram to pound conversion deserves special attention because it appears in almost every weight-based calculation. In the United States, we usually weigh patients in pounds, but medication doses are typically calculated per kilogram, so you will divide pounds by 2.2 to get kilograms. We will use that exact step shortly. For now, lock these 5 equivalents into memory because they are the bridge between how patients measure and how medications are dosed. Now we reach the key tool of the entire lecture, the basic dosage formula. Look at the equation at the top. Desired divided by have times quantity equals the amount to give. This one formula, often shortened to desired over have times quantity, will solve the large majority of calculations you have. It's worth memorizing, and it comes straight from the standard clinical references. Let's define each piece because understanding the terms is what makes the formula reliable rather than mysterious. Desired is the dose the provider ordered. It's what you want to give the patient. For example, 500 milligrams. Have is the strength you have on hand, meaning the concentration of the medication available to you. For example, 250 milligrams per tablet. Quantity is the form that the have strength comes in. For example, 1 tablet, or for a liquid, the number of milliliters that contains that strength. Here's the single most important rule for using this formula correctly. The desired and the have must be in the same unit before you divide. If the order is in grams and the label is in milligrams, you convert first so they match, which is exactly why we practice conversions. Once the units match, you simply divide the desired dose by the strength you have, then multiply by the quantity, and the result tells you how much to give. On the next 2 slides, we will put real numbers into this formula, once for tablets and once for a liquid, and you'll see how this works very quickly. For now, memorize the formula and the meaning of each term. Let's put the formula to work with a real example using tablets, and I encourage you to solve it along with me on a separate sheet of paper. Read the order in the dark box. The provider orders 500 milligrams. On hand, you have tablets that are 250 milligrams each. The question is, how many tablets do you give? Now we work through it step by step, and these 4 steps are the exact routine to follow every time. Step 1, check that the units match. Here the order is written in milligrams and the tablets are in milligrams, so they already match and no conversion is needed. Always do this check first because a mismatch is where errors sneak in. Step 2, set up the formula. Desired is 500 milligrams. Have is 250 milligrams. And quantity is 1 tablet. So we write 500 divided by 250 times 1 tablet. Step 3, solve. 500 divided by 250 equals 2. Then 2 times 1 tablet equals 2 tablets. Step 4, and never skip this one, check whether the answer is reasonable. 2 tablets of 250 milligrams each is 500 milligrams total, which is exactly the ordered dose, so this answer makes sense. The answer is 2 tablets. Notice how nice and orderly that was. Match the units, set up desired over have times quantity, solve, and check for reasonableness. That routine turns a word problem into a few simple steps. On the next slide, we apply the same routine to an oral liquid where the quantity is measured in milliliters instead of tablets. Now the same routine for an oral liquid, which is where the quantity is a volume in milliliters. Liquids can feel trickier, but the formula handles them the exact same way. Read the order. The provider orders 250 milligrams. On hand, you have a liquid whose strength is 125 milligrams in each 5 milliliters. Notice that the strength has two parts, an amount of drug and the volume it lives in. The question is, how many milliliters do you give? We follow the same 4 steps. Step 1, check the units. The drug amount in the order and on the label are both in milligrams, so they match and no conversion is needed. Step 2, set up the formula. Desired is 250 milligrams. Have is 125 milligrams. And here the quantity is 5 milliliters because that's the volume the strength comes in. So we write 250 divided by 125 times 5 milliliters. Moving on to step 3, we solve. 250 divided by 125 equals 2. Then 2 times 5 milliliters equals 10 milliliters. Step 4, check for reasonableness. 10 milliliters of this liquid delivers 250 milligrams, which matches the order, so the answer makes sense. The answer is 10 milliliters, and you would measure it with a proper oral syringe or dosing cup, not a household spoon, as we had discussed. Notice that the only real difference from the tablet example is that the quantity was a volume. The formula, the steps, and the safety check are identical. There is a second method for dosage calculation called ratio and proportion, and it's worth knowing for 2 reasons. First, some people find it more intuitive than the formula. And second, and more useful for everyone, it gives you an independent way to double check an answer you got from the basic formula. Using 2 different methods and getting the same result is a powerful safety habit. Here's the idea on the left. You set the known strength equal to the unknown dose as 2 ratios, then you cross multiply and solve for the unknown. Let us prove it using the exact same liquid example from the previous slide so you can see the 2 methods agree. Look at the steps on the right. We know from the label that 125 milligrams comes in 5 milliliters, so we write 125 milligrams equals 5 milliliters as our known ratio. We want 250 milligrams in some unknown number of milliliters, which we will call X, so we write 250 milligrams equals X milliliters. Now cross multiply, meaning multiply across the 2 ratios. That gives 125 times X equals 250 times 5. The right side is the 1,250. So 125x equals 1,250. Divide both sides by 125 and x equals 10 milliliters. That is the very same answer we got with the basic formula, 10 milliliters, which confirms our work. You do not have to use both methods every time, but when a calculation feels high stakes or unfamiliar, running it a second way is an excellent way to catch a mistake before it reaches the patient. Now we apply our skills to weight-based dosing, which is especially common with children and is exactly the kind of calculation where errors are most dangerous, so we take it carefully. Read the order. The provider orders 10 milligrams per kilogram per day. The patient weighs 44 pounds. The question is, how many milligrams should the patient receive per day? Here is where our kilogram to pound equivalent becomes essential. Step 1. Convert the weight to kilograms because the dose is written per kilogram, but the patient is weighed in pounds. Divide 44 pounds by 2.2, which gives 20 kilograms. Getting this conversion right is critical because an error here carries straight through to the final dose. Step 2. Multiply by the dose per kilogram. 20 kilograms times 10 milligrams per kilogram equals 200 milligrams per day. That multiplication is the heart of weight-based dosing. Step 3. Check reasonableness. 200 milligrams for a 20 kilogram child is consistent with the ordered 10 milligrams per kilogram, so the math holds together. Step 4, and this is a professional habit worth building, confirm the result against the medication's safe dose range in a reference and verify before anything is given. Weight-based doses should always be sanity checked against recommended dosage because a decimal slip or a missed conversion can produce a dangerous number. Notice the pattern. Convert the weight, multiply by the per kilogram dose, check reasonableness, and verify. For a child, that verify step can prevent serious harm, which is why we emphasize it so strongly. We finish with the step that separates a safe practitioner from a risky one, checking your work. A calculation is not done when you get the number. It's done when you have confirmed that the number is safe. Here are 5 habits to build, and they only take a second. First, match units first. Before you calculate anything, make sure the order and the label use the same unit, converting if needed. Most calculation errors trace back to a unit's mismatch, so this first step prevents the majority of them. Second, ask if the answer is reasonable. Develop a feel for a sensible dose so that a result telling you to give a whole bottle of liquid or a large handful of tablets immediately makes you stop and recheck. Your common sense is a safety device. Third, use a second method. For anything high stakes or unfamiliar, confirm your answer using ratio and proportion, or ask a colleague to check the math independently, which is standard practice for high-risk medications. Fourth, write your numbers safely. Always use a leading zero, so 0.5, and never a trailing zero, so 5 rather than 5.0. These decimal habits, drawn from medication safety guidance, prevent the tenfold errors that cause some of the most serious harm. Fifth, verify when unsure. If an order is unclear or your answer does not sit right, you clarify with the provider or pharmacist before giving anything. Asking is always the professional choice. Put these 5 habits together and you have a reliable safety net. In medication math, the goal is not to be fast. The goal is to be right every time. And these checks are how you get there. Okay, lecture summary. First, most medication math uses the metric system. So become fluent with grams, milligrams, micrograms, and milliliters, since these are the units you will handle every day. Second, converting within the metric system happens in factors of 1,000, And the direction is easy to remember because converting to a smaller unit gives a larger number, and converting to a larger unit gives a smaller number. Third, the workhorse of this lecture is the basic dosage formula. Desired divided by half times quantity equals the amount to give. And it solves the great majority of oral tablet and liquid problems as long as your units match first. Fourth, for weight-based dosing, which is common with children, remember to convert pounds to kilograms by dividing by 2.2 before you multiply by the per kilogram dose. And fifth, wrap every calculation in safety by matching units first, asking whether the answer is reasonable, using a second method or a colleague for high-risk math, writing numbers safely with leading zeros and no trailing zeros, and verifying with the provider or pharmacist whenever you are unsure. Remember that we deliberately kept this lecture to oral and weight-based calculations and did not cover intravenous medications. The most important message is this: accuracy is safety, and a calm, step-by-step routine beats speed every time. Practice a few problems each day because this skill grows with repetition, and soon these calculations will feel routine. Still struggling with dosage calculations? Check out some of the references I used for this lecture.